Imagine a hard disk. It's in good health and it's integral. It's made of folders. Every folder can include some files and other folders and so on. I can make a hash of the whole hard disk easily. And this gives me a photograph of the state of the disk. And I can compare this with a backup copy and see whether the backup copy gives me the same hash. But if I produce it, I don't have any indication of what's been changed. I know it's been changed, so it doesn't help very much. It allows me to know that it's not the correct copy. But we can go with another technique, which, for instance, is that for each folder, we create a hash. And the previous folder contains the hash of the hashes of the other folders, recursively. At that point, I keep the whole of the structure of the hashes. When I make the comparison, at the beginning I see it's a better drawing. This is the tree. Each branch of the tree has a hash of all the files in the folder. This has the hash of all these files. And this has the hash of all the hashes in the folders, and so on, step by step. So this gives me a root hash, which contains the hashes of the previous folder. When I go to compare this with another structure of a hard disk, I can see the root hash is different. Something has been changed. So I can go more deeply. So I can see that this hash is the same, but this is different. So at which point I know where the branch is that contains the difference. So I don't have to look at the whole disk. So I can look here and go to this branch. I see that this hash is different, but these hashes are the same. So I found exactly where the variation is. This is a tree of hashes. It's called a hash tree. This brings with it the complexity of having to take all the hashes together. To make the comparison, I have to save all the hashes of every folder. How big is this amount of data that I need to make the comparisons? It's quantity of data that grows linearly with the number of branches of the tree that I want to control. But there's a technique which is very different, but the same principles, which starts from a binary tree of nodes. So if each node is a folder, folder 1, folder 2, 3, 4, 5, and 6. The consequence is that this is F12, F34, F56, F1234. It's symmetrical, so there must be another branch. So I have the last hash, which is the function of these two. what does this show? The amount of data that we have to take forward is less than the previous system. The previous system is known as a hash map. This is known as a B tree. I can show, creating this kind of structure to demonstrate a change. In reality, in the blockchain, we use this technique to make a demonstration to the contrary, not to see if something is different or valid, but to understand if a transaction is a part of that block. Because one of the important things is the concept of receipt. I send a transaction, I want to know if the transaction has been effective in the blockchain, not if it's just been taken in consideration, and that the node has taken it, and it's had an outcome, and that it forms part of the completed transactions. Clearly, to understand if this forms part of the completed transactions, I need to have the list of all the transactions from the beginning to the end. So, otherwise, how can I tell if that transaction has an outcome? With the technique of the Merkle tree, we can show that, without going into detail, much of the data is self-recovering. So potentially, if I have to show that F2 is part of this tree, instead of giving the whole tree, I just give F2, F1, and all this block here comes together in a root CA. The user outside, with a mathematical technique, can understand if F2 has taken part in the root hash. This method, which I've explained in a simple way, but it's the important documents that explain this. The Merkle tree hash is the basis of all the blocks of the blockchain. In particularly our blockchain T.R.I.N.C.I. Bitcoin has 1, Ethereum has 3, and we with T.R.I.N.C.I have 5. Each one represents the state of that type of aggregation of blocks. So to understand if a blockchain or transaction has taken part in altering all the database, there's a very efficient technique, which is not widely used because it's cryptographist stuff. With a few receipts, you have the mathematical certainty that it has entered into the totality of the transactions and that it has contributed to modifying the system. It's as if, in a few words, we have a basket of balls. I throw one in, and I want to know if that ball is inside. I can't see inside. It's not so simple. To do this, the system which manages the basket can give a hash of all the internal trees, and it can tell me, without your ball, this hash cannot be achieved. With your ball, we can achieve this hash. So I can show that your transaction has taken place. We've used this technique in various ways. Firstly, to demonstrate that the transaction has taken place. Secondly, and importantly, for the digital identity. What is a digital identity? In a straightforward way, it's the digital representation of a subject, but it's a digital representation with the ability to sign, because the photograph, is it a digital identity? Well, I could take a photograph and I could say I'm Andrea. It's not a digital identity. A digital identity is something that, as physicists do when they try and show us what particles are, let's see how they behave. If the digital identity is something, this something must be able to express itself so that it can be recognized uniquely. By all and only the proprietor can do this. So if this is a digital identity, it must behave in this way. All must be able to say, you are Andrea. Only Andrea can prove this. This is the first aspect. The second important aspect is to be able to deliver personal information, name, surname, age. No. Age is a piece of information that changes over time. Date of birth, yes. But maybe the email address, blood group, anything, any information that can be carried by a digital identification document. And as we have done in our digital identity called ARIA, this should be confirmed by somebody else, an authority that certifies that the identity document is correct. Why would we trust Andrea's document? Because he wrote it himself, or because some authority, maybe in his case the city or the nation, has certified that he has that personal data. If we trust him, it's because we trust the certificate that he carries. So another characteristic of this little box is that it should contain certificates which confirm the data. Andrea is free to invent himself a new name. He's free to call himself whatever he wants to, but it's his choice. But for the world, he is Andrea. If he wants to change his name, it's important that if he does it with an invented name, it'll be a problem. He needs somebody to certify it. The last thing is that this identity, for the protocols we've chosen, must be sovereign. What does sovereign mean? It means that no one gives it as an identity. But this identity is not like this. Somebody has checked you. If you don't buy a digital identity card, the smart card is given to you by somebody. So it's not your identity. It's somebody that identifies you, invents a key, and says, this is your key, your password, use it when you need it. This is a delicate question because thinking about it and thinking about distributed systems and what we've seen in the past, the problems of the centrality of the system, to have an organization that gives you that identity, that's the first point of attack to block the system. Because if you can do that, the whole detail system is broken. I have created a point of weakness. The identity must be something that grow like mushrooms. No central point where they're created. How have we done this? This area system. We'll talk about Merkle 3 and how we've arrived here. Once we've identified the characteristics that are fairly simple to understand and harder to achieve, let's imagine our Andrea. I'll give him as an example. Andrea goes to an off license. The off license says, give me a document, because I can only send to people more than 18 years. Andrea has to give him the residence, photo, name, surname, and information he may not want to give. He only wants to show that he has more than 18 years. But to have to do that, he has to furnish other data. This is a problem. It doesn't form part of what we consider is a correct digital identity. In fact, the Italian digital identity forces you to give information. You can choose which fields, but it has all the fields. The Italian system has all the data. We've redesigned this with Merkle 3. That is, if we saw that in this technique, I can create a tree of personal data. In which there is name, surname, sex, political party, whatever you want. Afterwards, when you set about producing a certificate of validity, because clearly Andrea is free to give the shopkeeper just his name or just his date of birth. But the shopkeeper wants to know that this information is certified. When you create a certification, which are very similar to signatures, it's a document signed by a superior body. It's signed all the document, not just a bit. So if I just take a bit, might be the date of birth, that piece is no longer compatible with the certificate because the certification of validation validates the whole document. So with Merkle 3, we can construct certificates that can be the hash of all the data and not necessarily the certificate of just the name or the information that he gives. All the rest, you just need the hash. I've got a certificate, it's valid for my name and surname, my address and the rest. But in reality, I give you the hash of the name, the hash of the surname. I give you the date of birth, clearly. I give you the hash of my political party. I give the hash of something else. Because the shopkeeper only wants this, just the date of birth. How can he verify that that date of birth is certified by the certificate that certifies everything with the technique of Merkle 3? The Merkle 3 technique means that Andrea gives the hash of his name, which the shopkeeper can do nothing with that. And to avoid brute force attacks, we don't even do the hash of the name. We do the hash of a piece of the name. So if he knows another Andrea, he could do a mash, but it could be the same hash and discover his name. But if the hash is of a random word, there's no way he can do it. The result is that he gives the date of birth clearly, and he can demonstrate with Merkle 3 that date of birth has been certified with other data by an Italian banking authority, for example. So he has an identity, a real digital identity where he can spend money. He can show he has the data. He doesn't have to show it to everybody, but just that which matters. Only that which can be verified within larger certificates. This did not exist in the world of certificates. We had to create it specifically to manage digital IDs much more efficiently. And because the blockchain, I'll show you quickly, we'll go into it later. Our blockchain has a specific name, HDSB. This stands for High Density Scoped Blockchain. High density, that in the blockchain, that within the blockchain, there isn't just the hashes of the information, as happens with Ethereum and blockchain, because as it's costly, they tend to just put the hash. But if you have a blockchain like Ethereum, which would only contain the hashes of the documents, HDoc, it becomes impossible to make a smart contract, which can take directions on the basis of information in the document. The information has been destroyed by now. There's just the hash. I can't do a smart contract. If he has 18 years, he can move money. Because of the contract that says that is not there. It's been compressed in a hash, which is irreversible. And so I won't give me this information. In our case, in HDSP, we put everything in the blockchain, including the personal data. So we can create rules that go to fish in the personal details, the date of birth, go and look at the companies, the VAT code, other codes that allow meal tickets. A series of conditions that become variables to be used within the smart contract. The identity that we have built is a protocol. It's not a software or an application. It's an open source protocol, which anybody can achieve this. If you copy this protocol, it's perfectly compatible with all smart contracts made within the Affidaty type blockchain. So, in summary, what does this mean? The root is this. I go on any portal. Let's take an example of how we make a digital identity. I create offline public and private keys. I don't go through any service. This sovereign concept. I make a random calculation on the client of my computer. I separate the public and private ones. I self-certify that the personal data is correct. I sign my personal data with the private key, and then I submit the transaction. I've signed my identity. It's no longer confirmed. I confirmed it myself, but I've begun to create it. So there's a place for the certificates which validate certain kinds of information. So if somebody goes and had a look at what happens to the information within the blockchain, we'll have a public key, the self-certified data, the X59 certificates, which certify partially or totally some of the data of the user. There's another part, an important part, which are the mandates, which fundamentally are certificates, again, which are as if they permit other users to carry out operations on behalf of somebody else. This because mandates are not used generally in administration. And this has led to the bad habit of sharing passwords so that somebody can work on your behalf. This happens, for instance, with accountants who have the smart card of a company with its PIN, but that's the identity of a company. So the accountant may have 5 or 6 companies. A good commercialist will use it correctly, but a thief who goes into the office can steal 5 or 6 identities. It's not what the accountant does with it, it's what other people can do with it. If someone had created a mandate for the accountant, as it's created, it can be reversed. So if I discover there's been a violation, a fraud, I can annul the mandate, and my identity I use for myself. If the mandate to the accountant creates a company, I can say, I didn't authorize you to do this. It's you who created the company. How can you deny this? How can you deny this if your identity appears? So this is how digital ID works within our system. This is a website. It's a public website. You can go visit it as you wish. It's ambiguous. I'll explain this because to create an identity, you can't just go exclusively here. This is the website of Aria. Here there's Aria. WordPress is made by WordPress. You don't necessarily have to pass here. This is a web component. If we look at the HTML, here's a tag. It's called Affidaty S.p.A. It's a portable tag. You could take this tag without modifying it. It's a web component, self-consistent, has its functions. And what does it do? Have we made a web component? Because the site that holds this component cannot get directly involved with the client who's using it. It's like an iframe. It can't see what the user puts in, but it can feel the effects. If I create a digital identity now, the site of Area doesn't know what I'm doing in this segment. It asks me if I want to get access with Aria or if I have an identity. I'll create one straight away. I'm beginning to produce on my own the data. From now on, I can produce offline. I produce a random public and private key. I download the PDF of the public and private keys. So I now have an identity. It's not registered anywhere, but the identity has this format. Why do we download a PDF? Because there's been no contact between client and server. I haven't said, stop, register me. Yes, you're registered. Your registration number is. Everything is on the client. And so produce a PDF with JavaScript. It's not easy, but you don't have to go through any bridge, any particular technique, so that randomly this copy of the public and private codes exists. So obviously I'm going to print this document so I don't lose it. But going back to what we said before, logging in is complicated in blockchain with a public and private key, because it's not that the users remember their identity. So even if it's the most secure thing, most scenarios, shorter times, just the name and the password, email and password. So what the system does, it begins to produce the first certificate. In the meantime, it sends me a proof. So it sends me a code that shows that I've received it. I've confirmed it. This confirmation produces a little bit of certificate. So it certifies the email, nothing else. Now we create a password. This password has an important value. It'll never be communicated to the server. No operation between what I'm doing and the server. It will be used as a symmetrical encryption key with the email to get the public and private keys, compress them and encrypt them. And this creates a draft of digital data, which without knowing the email address and the password has no meaning to anybody. At this point, this is sent to our server, which will use it to go to the next step, to complete the verification, and then Okay, I'll log out. If I now try and get back in again, I put my email address. I need to have the PDF from before to get in using public and private key. So I need to recover these public and private keys. I put my email address. The system does a first attempt and asks, does this draft data exist at this email address? Maybe, it replies. It gives a result. This is a byte array of data. It still doesn't know if the user exists or not, but so the byte array has already been sent to the client. The client has this byte array. Using the password, the client tries to decompress the draft of the data. If it manages, that means that it is him. So the public key has been obtained and the private key is still available to the draft of the data, but hasn't been pulled out. But the moment I have to sign, the system will do the same game. It'll pull out the stuff with the password, it'll extract the private key, it'll use it for the signature, and it'll throw it away. So there's never a moment where it's transferred to the server, it always remains in the client. So this is ARIA, understood as a system of authorization. So ARIA does not provide a login, it provides an auth in. Subjects make use of the public key, the signature of the public key, and if necessary, personal data, self-certified personal data, and a series of certified data from superior bodies, such as ARIA, which certified the mail, which sent a mail to check it and said, yes, we can trust this person. The email address is under that person's control. There are other certification systems. For instance, the opening of a bank account. Our structure, we'll talk about this in future. We can open bank accounts with all operators who work with this blockchain and instead in bank drafts through the control panel of the bank, they sign a transaction. So the transaction is signed by this system. The bank, when it opens the account, says yes. It certifies that I'm Luca, born in such a date, and the bank then signs the certificate. The certificate is attached to my details and then enters into your platform. And I want to consume services. Your platform has made some smart contracts, we'll see later. And these smart contracts, yes, to access these services, you need to have at least a certified name and surname. Otherwise, I don't accept you. Or I can accept you, it's your choice. So the smart contract can get into the details, the personal details of the person and the mandates. So I can say, in your world, you are an energy supplier. Maybe we talk about energy communities and energy accounts. I have 50 kilowatt hours and I say to Ricardo, you can use them for me. I don't give him my private key. I create a mandate for Ricardo, which allows him to access my account. When the smart contract gets the request of Ricardo to take 2 kilowatt hours, he would refuse it. Ricardo would refuse it because he's entering into Luca's account, but he has a signed mandate. So the smart contract says if this person has a mandate from Luca, he can do the operation. This is only possible if the blockchain has all the operation. Otherwise, you can't create these branches of identification. When we start creating identities for inanimate objects, which come in two forms, there are two big groups. The first are those capable of Turing complete calculations, and the others are inanimate objects which are incapable of anything. A painting is an inanimate object. If it could sign, it would mean that it wasn't a painting. So deliberately, it doesn't have ability to sign. It's conceived to be a physical object that cannot sign. These are two identities which are deliberately acceptable within the register, but they have little differences. The first is for machines that are capable of calculations, that have a software library written in Rust or C. They're not libraries written for us. Our softwares are well known, they're standard. So we don't have to, I don't have the SDK, I can't utilize this thing, but there's a protocol for the form of the transaction, and you just have to compile the data, add the signature, as has been conceived at the international level. Having said this, a computer today can sign. As you've seen with Windows 11, this signature in these machines is done with a TPM, as we saw before. The TPM is a model that can sign an operation without ever losing the private key, because it's never given it to anybody. So, looking at it from the point of view as how hardware signatures work, if this was the computer, a computer with the Ethernet and the model, the TPM module, TPM2, how would it work? How would the system work to sign? In the language you choose, you create an interface of security, a web interface with REST that enters into the computer's internal logic. Maybe the computer manufacturer makes a call to this computer. This branch of communications is property of, once we've overcome the protection of the device, we go inside the object. There's a library which allows us to communicate with the TPM. If this message, will you give me the signature? Sign it. But how can we take the signature outside within the internal security protocol? The interesting thing is that this signature is the same that I could produce on the browser. So in reality, I can create a wallet of these objects because we enter into exactly how our blockchain works. And differentiates from others. What's a wallet? In the meantime, there are concepts that we call configuration over convention. There are conventions that, if you accept them as such, give an immediate reply. The first is, within the blockchain, there are all the possible imaginable wallets. It's as if there were. What does it mean to say if there were? If this is the blockchain, as if it was a database, if I go to make a select by ID, this can reply null or row. The blockchain always replies row. It can't reply null. Not because we've done a trick, simply because the blockchain, if I ask the wallet, Andreas wallet, how is it? It it will say it's fine. There's nothing in it, it's never been used, but it's there. If I go to the database, it doesn't exist. But if I ask, it replies as if it did exist. This is an very important characteristic because it allows us to baptize the wallets with specific behaviors. If a wallet doesn't exist, I can't react with it. It's the chicken and the egg. At the beginning, we're aware of this limit. Many said we should initialize the wallet, so there was a call and a creation of the wallet. But fundamentally, it always had to be done. So if I want to work in a wallet, I have to create it. So to make this more efficient, the creation is not just implicit, it doesn't exist because the wallet exists. This has taken away half of the operation that has to be done within the core. Secondly, and this is important, the public key is the identificator of the wallet. So it's not that the public key is associated with the wallet. The public key is the wallet, precisely. So if this is the digital identity I've created, and this is my public key, this is my wallet. In the database, in the line that says what I've got, how much money I've got, and what are my personal details. So let's go to Affidaty's GitHub. Now, this is the form of a classical transaction. As you can see, it has a Json, which has two keys, data and signature. Data is a structure. It's a bit more complicated, but within it, there's the account, the nonce, the network, the contract, the method, the caller, and the args. In the new version, this is a bit different. It's just a repositioning. The account is precisely the public account that we're talking about. In examples you'll see later, the account can represent the address of the currency, but that depends on how the smart contract is written. But in reality, the account is that to which the transaction is directed. Nonce. It's very important, this, for double spending. But if today I have to make a payment, a repeat payment of 10 euros every 10 minutes, what happens? If this is my system that produces a TX, I have to do 10 payments of 10 euros. I make a cycle of 10 identical payments. I print 10 intentions to pay. Exactly the same. In reality, you can't do this in the blockchain. If you do it, it's a problem. Because I can copy a digital data as many times as I like. So if this was allowed, I could be the man in the middle who takes one of these payments, I copy it 10 times, and I spend it 10 times. So if I receive a payment and I can photocopy it, it's as if you're giving me a check that I can keep on cashing as long as I want to spend it. So this is a problem of double spending. But there are people who need to do this. So the nonce is done specifically to produce 10 transactions with 10 random numbers. The important thing is that you dirty the hash of the transaction. So you get 10 different hashes. They're not all the same. So nonce is a completely random number. If you make it the same, it may not cause problems. You can change a payment to change something with the same nonce. It doesn't matter. But in practice, you are asked to change it at every transaction. The network is important because our blockchain is a multi-network, which means that I can create stellar ecosystems to have a star of nodes that maybe is a network that deals with automotive, or network that deals with voting online, a network that, I'll draw it here, N1. So this is the automotive network N1. A network N2 dealing with supply chain tracking, N3 for the Internet of Things. The wallet of Andrea, where is it? It's in all three. All wallets that already exist are inside. So what happens? If I didn't try to identify the network, a transaction that was intended for here, I could spend it here. Why? Because fundamentally they're compatible. The wallet of Andrea in the automotive network, he says, move everything from me to him. But he only wants to do it in the blockchain, not everywhere. So the name of the network serves to isolate that transaction to that specific blockchain. These are all HDSP. They are priority addresses given to the others. We'll look at contract later because it's too vague at the moment. The same thing for method. Contract and method. Let's say every blockchain has a database that's done more or less like this. When I said we had to remake the database, it's an anomalous database. It's got these characteristics. It's as if it was divided into columns. Let's say the columns are the account IDs, which, to simplify things, just put as letters. And in the rows, there are the account IDs. The same IDs as the columns. It can be defined as a symmetrical database, but the definition doesn't exist. Maybe we can propose that ourselves. This symmetry allows us to do a specific thing. These are the public keys, A, B, C, D. Let's say Andrea A has his database, which is made up of one sole column and lots of rows for all the other users. So Andrea was a money, a currency. It was Andrea coin. The Andrea coin would have all these cells available for all the possible wallets that are within the blockchain, an infinite number of cells. At this point, I could know how many Andrea coins D has, because 100 is written there. B has 4. So I could ask how many coins does C have? None. So if I ask how many C has, I know it's none. It doesn't need to be written there. I can see there's nothing there, so I know he has no Android coin, but they exist. But C may not exist. He's never arrived. If I ask how many Android coins does Luca have, the answer is 0, because of the previous convention. How can we move this money? That's another place. Put it outside, but in reality it's inside to avoid confusion. It's a smart contract database. And here there are a series of smart contracts. A smart contract is a program written in WebAssembly. Maybe somebody. Really, they're written in Rust or Python, in Java, and then with routines they're converted into WebAssembly. It's in binary code, not in an interpreted language. It's very efficient, and fundamentally it's a program. Unlike programs, it has a library. It doesn't have a principal execution point. It's a library of methods, and every smart contract is made of method and arguments. So, smart contract 1, smart contract 2, 3, 4. When the A account is used for the first time, we can say from here to eternity, it's in a reversible act. The program that manages the database of A is the smart contract number 1. So let's go and analyze this as it is. I've got a database in which every row is a potential account ID, and associated with this is tied irreversibly to a software contract made up of methods and arguments. It's arbitrary. There are no rules about which methods and arguments to be used. So, going back to the schema of the transactions, the contract is the hash of the program I want to launch. It's optional because normally you don't say I'm going to launch this contract, but the user who's compiling the contract, as the smart contract is already within A, you don't have with every transaction to remind it to use A, because the owners have put it there. But I can make a limiting operation. This is important. I can limit this transaction only to that account with that smart contract. So it's as if that account manages crowdfunding for a hospital. It wants to collect money for that hospital, prepare a transaction that says, what smart contract? This is okay. Do the hash. It's easy to do this. It's easy to do with a smart contract. You can ask the blockchain what contracts are available. You do the hash and say, yes, you can do the donation, but I write the hash. So if at this moment in your account the hash is there, the movement will pass. But if it's not a smart contract of crowdfunding, it's your account which is taking money for others, the transaction becomes refused. So if we at Rosella, seeing how much traffic there is, we make a voluntary association to raise money to send to Biafra, and we put it in the name of the bank account of Luca Vignali, who makes the donation, doesn't have the certainty of the destination of the money. It's Luca's account. Luca will do whatever he wants. In this way, I can collect a transaction and say, I will give you this transaction. as long as it's for the no profit. That there are the rules of the onlus, that the crowdfunding rules that I'm agreeing to. In this case, the transaction is valid. If in the blockchain there isn't the smart contract, it'll be refused. So this contract, even if it exists for a specific application, it's optional, because if you don't put it, you take the default. If you put it, you don't get another. You're saying, I want it that it's like this or nothing. This is a delicate passage. Clearly, method. Then, if the smart contract is an application, which method do I want to call upon? And who is the caller? He who wants to carry out this operation. Luca Vignale. I'll have the curve, the public key, and whatever. The arguments. As it's a method, we can go to the arguments. Transfer 100. Transfer is the method. The arguments are the arguments of any sort of method. Finally, the signature. What I want you to see is that data and signature are the only two real arguments, because data is an aggregate of information. Signatures is done on all the data. Because of reasons of recursion. Because if I have the data and I sign it, I've contaminated the hash and I have to start again. So if I separate them in this way, this signature is only valid for this group of arguments. So let's take an example. This is a public key. There's the random nonce. There's the name of the network, the hash of the contract. The method is terminate. The caller is AGDSA. These are the arguments, which you can see in a binary fashion. And then the signature. In this case, I've called it the terminate, which you might expect a Boolean or something, but I turn inside the arguments, which is a byte array. This is very important. There's no argument number 1, number 2, because the data is all compressed by message park. Message park is a serialization protocol for data. Every language has its serialization, but we don't want to be limited to the world of Rust for the use of this stuff. So there are third-party libraries that offer very efficient systems to compress data with a kind of Esperanto. Could be photo buffer, message park, Json as well is a system of compression of homogenization of data. Message park seemed to be the most efficient. From a series of tests that we made, message park is available in 3 or 4 programming languages, so it's not something we invented. So what happens if our method was if this is my application and the application has within it terminate and as a parameter it waits for the number of attempts, the value, the weight. The function shouldn't be written like this. It should be written in args. This is a single argument. There are utilities which allow you to do n, t, p. Let me put it clearly like this. Let VA and P be equal to message pack of args. So you extract the arguments from in the required format. The was machine that we use inside the core to run the smart contracts, we designed trying to be agnostic towards programming languages. So it means that if Python does the strings one way, trust another, the trust codes objects with a meaning with one way, like dupla, which don't exist for others, it would have been a disaster to make these things exist together. In reality, this disaster hasn't happened, but we have to accept a limit, a physical limit, which is how the was machine works. I'll explain briefly here. The was machine works like this. There's the core. This is the was machine. It's the machine that runs the smart contracts. It's a smart contract machine. Here's the memory. Practically, whoever invented the was machine, it wasn't us, but it's a whole world of WebAssembly. The only format that the smart machine will accept is whole numbers. So paradoxically, when we approached this question, this application, we asked, how can we do this? Is it complete? Have they done tests with whole numbers and then they were going to strings? No, they stayed there. And who made the was machine? Said, you do our application, you must only use whole numbers. You can make a calculator and nothing else. You can make smart contracts, but you can't do smart contracts that interpret objects or other things. The motive is simple. And they did it for reasons of efficiency. In reality, it works like this. The core can get access to the memory. The memory can be accessed by the smart contract. When the core wants to pass 4 or 5 arguments to the was machine, what does he do? He makes a message pack of these arguments. He obtains a vector of bits. He sends the vector, and so he has an offset in which he has written and a len, which are made up of whole numbers. At that point, the core recognizes the whole numbers that represent the arguments, calls this was machine, get going, run, invoke method, terminate. It doesn't pass the arguments you made during the transaction. It passes the offset and the len. At this point, the method enters, goes into the memory, the offset, ends in the len, takes the data from the message pack, takes them within the application, analyzes them, and has whole numbers, strings, in the format which you have chosen from the beginning. If it was a string written in Python, and the application is in Python, you find a string in Python. The system is very efficient. You don't have to make 4 or 5 or 6 arguments. So the only possible argument is the arguments. If you have 4 or 5 or 6, it is established during the compression in message pack. So what gets passed is the message pack blocked. The signature, what is this? The signature of the hash of all of this and the args It's a signature of the data, which is put out externally. What is the wildcard of the transaction? The transaction is created in the client or in the place in which it'll be signed. Normally, the application doesn't just wake up and say, let's do a transaction. No, that would be madness. No, there's somewhere, then a web page, an application. This says, sign this, please sign this, otherwise I can't go further to launch the application. So here I have an app. It's a generic app on web or in a device. It submits this to the user, the unsigned document with a prepared transaction. It, via ARIA, adds the signature. And at this point, this document is passed to the core in the node. The node carries out a first control. It checks that the signature is compatible with the system. If not, it rejects it. Otherwise, it takes it in consideration and supplies a ticket. This is a synchronous system. There's no synchronous blockchain, because if it was synchronous, it would mean that we had renounced the R.P. paradigm. I say, I've taken in consideration this transaction. I promise that I'll send it on. This is the ticket. It allows you to do polling or streaming, depending upon how you want to organize the application, to find the output of this transaction. But if it's rejected asynchronously, because the core refuses it immediately. It doesn't submit internally. If it has passed synchronously, I get a ticket as an answer from the REST call. Straight away, I put the ticket at the bottom of the list of tickets, and I say, when I have a reply, give it to me. What journey does this transaction take? It's pushed in the unsigned transactions. A block is produced. There's a negotiation for which block is taken forward. All the transactions are carried out. And when this transaction is carried out, there are 100. This is the 32nd. Straight away, the reply to the ticket is sent as the outcome of the method. If the method says OK, perfect. OK is sent back to the ticket. And so this socket, which, for example, you have submitted, which has pub sub logic, published subscriber logic of the events within the node. I am associated with the event of the ticket. When it gets to me, I have an event which sends me the socket, and it tells me that the result of the transaction is true. Okay, I take note of it. At this point, the block is propagated and closed, and we move on to the next block. What these smart contracts do is your business, which you should find within this system of blockchain. The blockchain is fundamentally built on new rules. If you want to use old rules, we provide 10 oven-ready smart contracts, such as basic asset. If it works, you don't have to invent a coin. Maybe we can embellish it with some additional functionalities. Maybe you can say, if I move this only within the user with a certain certification of belonging to my congregation. So if you're not part of this company, you can't have my coin, for example. Or you can create the escrow account with which I create non-fungible wallets where you can push like you want. There's no way of getting the money out of it. No private key can open it. Only the mathematical combination can unblock it. You have to revive at a certain value. You have to have 5 people who've undescribed. Lots of conditions have to be satisfied. In crowdfunding, for instance, I need $1,000 to do this operation. If I get within December this, otherwise I send the money back. This is a classical smart contract. I put the money, when I get €1,000, the smart contract has changed its conditions. The money can be taken away. Otherwise, they're blocked inside. To do this, I create a method, I do a transfer, and the transfer has if. amount is greater than a given number, then go. Otherwise, it stays inside. This is something we'll return to later. What, in general terms, is the consequence of the execution of a smart contract within a blockchain? What is the itinerary of the execution of a smart contract? Here we have, in broad terms, here we have a broad outline of how the database is structured with all the core of the application. We have storage, which is a database. We have a part for communication, which deals with the pub sub. We have a consensus model, which is flexible. It forms part of, with a technique which we call bootstrap, which allows fundamentally for a network to be sure that everybody within the network are behaving within the rules. If they don't respect the rules because they change them, they change the hash of the network, so they become people who are no longer able to transmit information until they update the software. It's as if the email sent by Windows 10 was not accepted by Windows 11 until Windows 10 was not updated to Windows 11. So this internal technique protects the system. We have the SDKs written to date in 2 programmable languages. We have an important environment in which the node can be tested, made of elements such as Docker, which allow a node to be set off in debug mode to see the effect of a transaction within the blockchain, to see in real time if the data can be moved, what logs are there within the operation, because as with all applications, we have foreseen a log management and an event management. So clearly the management of the logs in operation is ignored, but the management of the events, no. The events are very important because the events are the summary of events which are added to the classic emit, for which the program becomes, let me say, if the program goes here, emit this signal, which is not just slowing down the function, but I can put management information, such as for every movement of money, this has changed the account, this is the receipt of the money, this has done an operation which I want to monitor. So clearly it's the smart contract which deals with these events. So if this is again the database which we saw before, A, B, C, D, E, the transaction we know modifies, A can only modify the data in this column. It can't change data here. Only B can do this. Somebody who moves the person responsible for the movement of these assets is the smart contract. As it can't be modified, there is the guarantee that whoever produced it will leave it where it is. So if I produce a basic asset and the only rules are the transfer, which allows the money to be moved from me to you if I am me, and this is the major rule of the basic asset, forever it'll be like that. It can't be updated or changed. But there are techniques for managing the versioning, but every version is a new application. It's not like Theorem where you can jump from one to another. The updates are made of the applications, but it is necessary to maintain back compatibility towards who has ever made a contract with those rules, which, right or wrong, will have to follow that. It can't be that I do a crowdfunding and the rule is if I reach this amount, I can take the money. Somebody changes the rule, says, no, if we get halfway, I can take the money. What happens in that case? No, somebody who had the old contract won't accept this. You have to keep to the old rules, the original version, which guarantees who underwrote the contract will work in that way. So, the smart contract, which lives within the database of A, has functions. For instance, transfer. A transfer needs a from, expects a to, and amount. And a message. Maybe a cause, motive. This is a method of A. This is A's coin. If I want to move money from B to C, Mr. C creates a transaction, call A, which is the application within that table. I say I want to invoke the transfer. The arguments are from, to, amount, and then there's my signature. When the application goes inside, it has the database available to it. How will the transfer be made? If ctx.call coincides with args.from, then go for it. If he says, this is exactly what I signed, you can make a step forward, go for it. Go and see if he's got it. If he hasn't, refuse the transaction. If he has, go ahead. Or, this is a basic asset. In advanced asset, we'll go into the mandate. If CTX call coincides with the from, or the CTX call is mandated from the from to do this operation, you can go ahead. So if you go ahead, this gets access to the only available portion of the database, sees all the coins, and can say B can move the money to C. The values that can be contained in this cell, bit arrays, so I can put anything inside, numbers, tuples, arrays, objects, anything. There's no limit to the amount of data you can put in this cell. If you want to put in a terabyte and you can afford a terabyte, then you can do that. There's no physical limit. It can be set, the physical limit can be set in the configuration, because the bootstrap, which you'll see at the end, is a kind of DNA of the blockchain. All the rules that can come to mind, such as who can create a smart contract, who can create money, who can create users. The fact that there's a set of configurations, Boolean or numbers. We've created an application, Bootstrap, which is executed when a virgin node comes to life. It takes in all the rules that are said to it. For this virgin node, we say it's baptized with it's bootstrapped. The hash is calculated. That hash determines the network of all the nodes that have chosen it. It's like the cartridges of the old video games. I have the console, I put in the video game, I put in the disc of the game. At that point, the machine, the PlayStation, has the network card, the video cable and the controller. What happens from then on depends only on the game. So if there are rules that say, are we sure that you can put any kind of data into the game, too big, too small? We propose a basic configuration, then somebody else can come along and say, I want to do my blockchain with limits on the use of data. I want to do Ethereum. I want maximum compression. A Bitcoin, 128 characters, for instance, which you can write inside. So I create a configuration for this operation. At this point, that bootstrap can be shared via open source, and the core of all the people who want to use your bootstrap becomes the game to put inside, which has new life on the blockchain with new rules, and all those inside and attached to that node will accept those rules. This is a subject that we'll talk about later. What I want to say in this moment is that here, in these cells, are byte arrays. This is very important because initially they were only numbers. That is in version 1 of the blockchain. They were just numbers. They represented only whole numbers. The problem becomes when we begin to manage much more sophisticated applications relative to Ethereum. For instance, luncheon vouchers. If these were the cells of the luncheon vouchers, and these are the accounts A, B, C, D of all those who have luncheon vouchers, if I put numbers in, A has 3 luncheon vouchers, B doesn't have any, C has 2, D has 8. But a luncheon voucher has an expiry, and the expiry so if I take any luncheon voucher, it says this is worth €8 and it expires on the 31st of December. This luncheon voucher is worth 5 and it expires on the 31st of January of 2021. How can I put that inside? It's complicated. So we began to substitute numbers with tuples. You know what a tuple is? Objects, let's say. So an object could be A has one of €8, which expires in December 2021, and C has one voucher of €5, which expires on the 31st of January. Rather, he has 10. At this point, what happens? These are not whole numbers, these are data structures. But who comes from C or other languages knows that we can implement sums. We can make the sum of an apple and a chair. This is the same as what we're doing here. I implement the sum of these structured objects. I can say if C gives 3 meal tickets to B, the smart contract says that the final outcome at the end, C will have 5 of €5 that expire on the 31st, and D will have 5 of €5 that expire on the 31st. If C gives a voucher to A, note this is 8 and this is a 5. So he'll have this one and another voucher for €5 that expires on the 31st. With numbers, we couldn't do this. With a byte array, we begin to create structures which, if they are compatible, they sum. If not, they vectorize one above the other. So with this structure, updating it to this version, we can open to a whole range of scenarios for smart contracts that otherwise you had to manage with tricks.